remember here's Aristotle, right? So Aristotle, or the Aristotelian view of thinking, says things don't move unless you push on them, unless you have a force on it, okay? And you say to yourself, that's right, look, see, when I stop pushing, stuff. And Aristotle would have said things have a natural tendency. If you leave them alone, if they're moving, you leave them alone. On their own, they have a natural tendency to slow down and come to rest. And that was true for 1,500 years. And nobody even questioned it. And so, but if I can see here, watch, you're not going to start moving until I push you. And if I do get you moving, you have a tendency to, see, it makes sense, doesn't it? Until Galileo came around. Now, Galileo came a whole lot later than Aristotle. Galileo, I think, if he hadn't had his personality he had, it would have been difficult for things. It would have eventually happened, but I don't think it would have happened during his time. And even during his time, he got in a little trouble with the church, mainly because they sort of thought he was portraying the Pope as being a simpleton. So I think he got in a little trouble there. But it wasn't that he was anti-church at all. That's not true at all. It's just that the Pope was in power, and that you can't have people going around making you look like, if you think the Pope was a fool, then they're going to lose some of their power. And so that was the whole idea there. They didn't put him in prison. They actually he was in house arrest. But a lot of his papers later were smuggled out of Italy because they didn't want him printing any of this stuff. A lot of his work was smuggled out of Italy, and that's how we actually know a lot more about Galileo. All right. Well, excuse me. And we talked about this twice, I think. Everybody okay on that page? So he's trying to show that if you just think about it, I don't think things have a natural tendency to come to rest. And he said, look at this right here. He said, if you're moving and you're going downhill, you speed up. If you're moving and you go uphill, you slow down. What if you're moving, you're not going uphill or downhill, then you would just maintain that speed. And then he says, when things go down a ramp and go back up, how far do they go? And they go until they reach the original height that they started at. Well, then if the second ramp was flat, then they would have a tendency to keep going forever and ever and ever. Yep. And boy, for somebody in the 1600s to say that, that's like, what are you talking about? That's not what I see. I never see that out here. And no, they didn't know anything about what would happen in space, but that is what happens in space, isn't it? When you're away from things like air resistance and friction, that is what we see. Okay, so you're all right on that. Now, I'll show you one other thing that Galileo did that kind of had this. People had a lot of trouble with this part of Galileo. It says Galileo also believed, like Copernicus did, that the Earth does not sit still. There are a lot of problems with the Earth sitting still, because you could actually look out in space, and yes, I saw the sun go across the sky, and I see the moon go across the sky, and I see the stars go around across the sky, and but there were some things out there that didn't fit the model of the Earth sitting still. And you said you talked about this in Humanities. Did you talk about epicycles? So one day you'll see these stars, and they're always like this. They're in constellations. You watch all night. Just watch all night. There they go. They look like they move across the sky. But then you'd see these other stars that were, maybe I saw a star right here. And the next night, he didn't go with me. You're over here, and then you're over here, and then you're over here. And how come you're not with the other stars in the constellation? And they called them wandering stars. And the word the Greek word Latin is plankton, like plankton wanders and planets. And they called them planets because they were kind of wandering stars. They didn't stay with their neighbors. And sometimes these wandering stars. Here's my constellation moving all night. My wandering star might be here, and then the next night it might be here, compared to these three stars. And next time, I said, what's that all about? And then what was interesting is, if it looks like it's moving this way, and then maybe the next night it might be back here, and then it might go back here and back. And it has some really weird patterns. And so the Earth sitting still just couldn't explain some of the motions of planets. And so they kind of come up with, the people who wanted the Earth to be the center, they come up with little things like this. Oh, well, here's what happens. These stars are really going like this, and then some of these stars that are going around the Earth, they go like this. Woohoo! Woohoo! Okay. And they take little trips. Instead of just going around the Earth, they'll go, woohoo! And that's why it might look like one day you're here, and then you go to the right, and then you're going to the left. They call that retrograde motion. Retro means backwards, right? And so they made up these little epicycles saying, well, all right, now it works. Now the Earth can still be the center, and now we explain everything. And anyway, so Galileo, after hearing about Copernicus, he said, Copernicus is right. You can explain all this as long as you have the Earth going around the sun. It can explain everything. Like I go around the sun at this speed, and you go around the sun at this speed. And you go around the sun at another speed. And that's why I might see planets be here, here, here. And that would explain everything. So, anyway, what do you think they said? Hey, Parker. What do you think their biggest argument was for Galileo when he says, no, I think I'm on a moving planet. Not only is it moving at tremendous speeds around the sun, it's also rotating at tremendous speeds. What do you, Eli, can you help me out, please? Eli, close the door, please. Now, what do you think their biggest argument was for Galileo? Galileo, you really want me to believe that we're on a planet moving at this unbelievable speed around the sun, and we're moving at a very high speed in rotation. What do you think your argument was?
Why does the sun move so slow?
Say it again.
Why does the sun move so slow?
Why does the sun move so slow? Well, he would have said that the sun doesn't really quite, quote, move. If we actually are doing this. So here's the sun, and sunrise, moon, like that. So that's the speed. Even though we think it's slow, we actually go about, if you're at the equator, you go 25,000 miles in 24 hours. So that means relative to space, you're moving at over 1,000 miles per hour relative to space. So Galileo didn't think that was slow. It's just that it's a big distance. What do you think another argument would be? Think about this. What is it?
We're not moving.
Because what now?
Like everything's still.
They said to themselves, don't you think I would know I was on a moving object? Don't you think that I would realize that I'm moving at this high speed? And wouldn't you think I would feel myself rotating? And what would Galileo have said there? Yes?
Oh, so everything's moving at the same speed.
Now, I've mentioned this to you before. If you've been in a plane and they bring you a drink and you sit down there, and did you ever say, I don't know if I want to put my hand in front of a can of Coke going to 800 miles per hour. And it is going 800 miles an hour relative to the Earth. But everything in that plane, you, the Coke, and the air you're breathing is moving at 800 miles an hour. And so it really appears as if nothing is moving. And that's what he had to convince them. He had to convince them that it's all about relative. It's all relative. Motion is relative. Here's a big argument they had. Galileo, see a bird way up there on the limb there, 50 feet up in the air? When the bird goes down to catch a worm, won't the Earth have rotated out from underneath him and he'll miss the worm? Because by the time he gets there, the worm's not there anymore. I'm gone. Galileo, how do you explain that? And Galileo, I've seen a bird catch a worm. That doesn't make sense to me. Galileo, when I drop a ball from a building, tall building, by the time it gets to the bottom, wouldn't the building have already moved? And won't the ball run into the side of the building? And you're saying to yourself, that's right. That's right. And I used to remember when I was a kid thinking, why don't they just take a helicopter, and go straight up, let the Earth rotate, and come back down to China? And he said, wait a minute, I thought that too. So Galileo is going to be talking about things like this and try to explain it. And inertia is going to be one of the things he's going to talk about a little bit. Yes? All right, so here's Galileo one more time. Frames of reference. He said motion is always has to be talked about with some kind of a frame of motion. Now, you and I, the most common frame of motion that we have is the Earth's surface. So if I see this, go over here, you're going to tell me it's moving because this and the Earth's surface, and you're going to say it's moving relative to the Earth. You know, right? What if you were lying in bed at the equator and for 24 hours? Are you moving or not moving? Just lay still for 24 hours at the equator. Are you moving or not moving?
Relative to what?
Now, if I had some person sitting next to you, they say, no. I watch them. They did not move at all. But somebody who's on the moon with a powerful telescope, whew, man, I saw you move behind my telescope at over 1,000 miles per hour. Are you moving or not? It's all relative, and it's relative to what frame of a reference you have. When we do start making a jump and start going to other planets or things like that, we have to have a new way of talking about motion. If we leave the Earth, we have to have a new frame of reference. Do you understand that? Because you could be there. If you have no frame of reference, you say, well, I think we're moving. What do you mean moving? How do you know we're moving? Well, my instruments say we're going this fast. Really? Compared to what? And they have to be compared to some frame of reference, right? Like they might have a line between the planet and the moon, let's say Earth and moon. If they draw a line there and you know that you're moving this many miles per hour, they could say you're going that many miles per hour. But what if you don't have a line? What if you're saying, go that way, and there's nothing there? There's no planets, no moon. How fast are you going? And again, relative to what? What am I relative to what? So that's what the biggest thing that Galileo had to overcome is people had this idea that I would feel myself moving if I was on a moving planet. And by the way, I don't know if you understood the dropping a ball from a tall building. I don't know if you understood it or not. Galileo would have told him this. You know that you're at the top of the building, and do you know what that ball's doing before you drop it? You know what it's doing? It's moving. Now, it's not moving relative to the Earth's surface. But again, if I'm not on the Earth's surface, I'm looking at the Earth, I'll see a person, I see a building and a person and a rock go by me at about 1,000 miles an hour. So the rock was already moving, and the rock and the building were both moving this way. You see that? Then you dropped it. Now it started going down. But did it lose its inertia? Watch now. Did it lose its inertia to want to keep going that way? No. That ball still wants to go that way at the same speed, but it starts going down. So it does two things. And it actually goes like this. It'll go. Now you might think it's going to end away from the building. No, because what's the building doing? So it would have been the inertia of the ball that before you drop it, when you drop it, it still has a tendency to go that way. Let's take a look at the worksheet I gave you. And, wait a minute. Is that the one? Okay, I guess that's not quite the one I wanted. All right, I know. Let's take a look at this worksheet. Now, this is not for a grade, but I'm going to go down the row. Sarah's going to start. And I don't mind if you miss the question. I just want you to think about it. And this has to do with mass, weight, inertia, that kind of stuff. And let's see how well we do on this. All right. So go down to number, let's see, where the first question is right here. It says here, learning physics is learning the communication, connections between concepts in nature, and also learning to distinguish between closely related concepts. Velocity and acceleration, which are treated in the next chapter, are often confused. Similarly, in this chapter, we find that mass and weight are often confused. They aren't the same. Please review the distinction between mass and weight in your textbook to reinforce your idea, blah, blah, blah. So let's try the first one, Sarah. Compare the concepts of mass and weight. One is basic, fundamental. depending only on the internal make of the object and the number and kind of atoms that compose it. It is, this is a concept that's fundamental. Which one is that? You think we're talking about mass or weight there? What's the most fundamental? All right, I agree. That's good. All right, Parker, you read the next one.
The concept that additionally depends on location and gravitational field is weight.
Okay, you had a 50-50 chance, didn't you?
Yes, actually, I did.
And so what happens is I can take a kilogram on the moon, I have a kilogram on the Earth and a kilogram on the moon. It's still a kilogram of mass, isn't it? But if I had my spring scale with me, it wouldn't weigh the same on the moon, would it?
It would
So
not.
it does depend on the gravitational field. Next one,
I knew it was weight then.
Colleen. Blank or blank is a measure.
Blank is a measure of the amount of matter in an object and only depends on the number of kind of atoms it composed.
What's your answer again?
Mass.
Good. Very good. I don't care if you miss these, you're just trying them, okay?
Well,
Let me show you.
kind of basic.
Correctly, you said that blank is a measure of laziness of an object.
Laziness means a tendency, if you're at rest, to stay at rest, and motion to stay in motion.
Is it weight?
Which one?
Weight?
Okay, what do you think?
No.
Well, and let's think about that. I will tell you this, inertia, mass is a measure of inertia. Like if you have more mass, you have more tendency to stay at rest or more tendency to stay in motion. So I always think of mass and inertia like that. They're pretty much kind of the same thing. Mass and weight are not the same thing. All right, so this would be said, this is called mass, also known as inertia. Next one.
Blank is related to the gravitational force acting on the object. Weight.
Okay, next one. We'll go back up here. Patty?
Weight depends on an object's location, whereas mass is not.
So what's their first blank?
Weight,
Weight depends on location. What about the other one?
mass.
Okay, next one.
Well, she read ahead. Oh.
Reading.
Oh.
Okay.
In other words, a stone would have the same blank whether it is on the surface of Earth or on the surface of the moon. However, its blank depends on its location.
What's the first one?
Mass,
Next one.
weight.
All right, next one.
Oh. Got lucky.
Am I next?
Yeah.
No.
On the moon's surface, where gravity is only about 1/6 of Earth gravity weight. Of
What?
weight.
Like,
What?
Well, the answer is either mass, weight, or both mass and weight.
It's out of three. Okay.
They tell you that gravity is different on the moon than Earth, but they want to know which property of it would be the same on the moon as it is on the Earth.
It would be the same. Okay, the mass. The weight changes because of the gravity.
Right. Good. Next one.
While mass and weight are not the same, they are inversely proportional.
What do you think? Everybody like that one? So that means the more mass you have, the less weight you have? What? Okay, what do you think? All right, that sounds good. All right, next. And you know why? That's why people kind of interchange those two words, because if you have twice the mass, you also have twice the weight, don't you? That's why people think you can interchange them, but it kind of gets weird when you go out in orbit, for example, and you have mass, you have no weight. Now what happens, you know? It has a lot to do with the gravitational field. Next.
International System Unit, SI units of mass is blank, and the SI unit of force is blank.
Okay, what do you think the SI unit for mass is?
Kilogram.
Yep,
And then Newton.
and a Newton, right? Okay, next one.
In the United States, it is common to measure the mass of something by measuring its gravitational pull to Earth, its weight. The common unit for weight in the U.S. is the pound.
Okay. All right, let's go to the next one. All right. Objects with mass also have weight, although they can be weightless under special conditions. If you know the mass of something in kilograms, you want to change its weight in newtons on the Earth's surface, you can take advantage of the formula that relates weight and mass. And mass, the weight is equal to mass times the acceleration due to gravity. And we're going to study little g in this chapter. Right now, you're not sure what that is, but mg, whenever you hear a physics person say mg, you know they're talking about weight. So you take the kilograms, now watch what's happening here. If I take kilograms times the unit for acceleration, and we're going to talk about acceleration in chapter 4. The acceleration units are meters per second squared. So if I take mass times acceleration, I will get kilogram meters per second squared, which is called a Newton of force. So you're going to have to memorize that. A Newton is a kilogram meter per second squared. All right. It just so happens that we will, not this next chapter, but the one after it, we'll hear about Newton's second law of motion, F equals ma. And if you think about it, if you take the mass in kilograms times acceleration in meters per second squared, that will give you newtons, which is force. Okay, let's go over here now. In number 1, it says, what is Felicia's weight in newtons? Well, how much is she? She's 45 kilograms. Whose turn is it? Every little calculator? And what I want to do is, Earth's gravitational constant, even though it's actually 9.8 meters per second squared, because we're just starting this out, I want to use 10 meters per second squared. Is that okay with you? That'll make it easier to do your math, okay? All right, what is her weight in newtons if her mass is 45 kilograms? Say it again. 450 what? Yes. Okay, next. Ben.
Given that 1 kilogram of mass corresponds to 2.2 pounds at Earth's surface, what is Felicia's weight in pounds on Earth?
So this one you might have to have a calculator, but it says that 1 kilogram is how many pounds?
2.2.
And she's 45 kilograms, so if you have a calculator with you, you can take 45 times 2.2.
99.
Okay, 99 what?
Good job, Ben.
Pounds, LBS.
Okay. All right, next one. Back up here.
Good job, Ben.
Number 3.
Yeah. Yes.
What would be Felicia's mass on the surface of Jupiter?
Okay, now, what we have to do is... Wait a minute. We don't have that here, do we?
Well, 4 is a copy of 3. Just
Where is it?
4 and 3 are the same question. Well, one's
Okay,
not-
so what we find out here is the acceleration due to gravity on Jupiter, because it has more mass, is bigger than the Earth. Instead of being 10 meters per second squared, it's 25. So how do you find weight? Weight equals mass times that planet's gravitational constant. So what do you think on Earth? What would Felicia's mass be on Jupiter?
Be 40.
Oh, I'm sorry. I actually don't use this till the next question. Sorry. What's the mass on Jupiter?
45
Yes, 45 what?
kilograms.
Because that didn't change, does it? Okay, next one's where you need a calculator. What would be her weight on Jupiter, knowing that that planet's gravitational constant is not 10 meters per second squared, but 25? One more time. Newtons, right? Okay. Different masses are hung on a spring scale, calibrated newtons of force on Earth for 1 kilogram. 1 kilogram is about 10 newtons. Next one. Alistair, how about 5?
The force exerted by gravity on 5 kilograms is 50 newtons.
Okay. And they're directly proportional, aren't they? Back up to Sarah.
What's easy?
The force exerted by gravity
So how many kilograms would weigh 100 newtons? Yep. Hi, Parker. Oh, wait a minute. Okay, make
Oh, I get to make it up?
Yeah,
Okay,
yeah.
I want to say 10 and
No, we're just 10. Do another one.
cheating.
Here, I'll make one up for you. All right, make one. Ready? 3.5.
Ooh. Wait, 35.
Okay, all right, very good. All right, that's it. All right. Okay. Anyway, this sheet here, I didn't want to do this for a grade. I just want to do it as kind of like a review a little bit. So I'm going to put that one up. All right, I'm going to go as far as what I was trying to talk about here. Let's see here. The rest of the chapter, I'm going to kind of, we've already done these. We already know what mass is and what weight is. And so I'm going to kind of go over this. I don't want you to completely forget about it, but here's the one I want to go to now. This last page, this is what's very interesting. And again, this is what Galileo would have had trouble convincing people with. I'll bet if you were to go like this, take this rock and just kind of go like this. And if I took a video of that, you just see the rock go up and down, up and down. Now I want to imagine that, what if I'm in a car, a glass car, you can see all the way in the car. I'm in a glass car, and we're going at about 30 miles an hour down the road. So we're going 30 miles down the road, and what I did is, instead of a rock, I have a light-up ball. So I have a light-up ball, and it's nighttime. Okay, so if I'm sitting still, and you watch the light-up ball, you see it go up and down, up and down. Now the car is going at 30 miles an hour, and I go like this. Will it still land in my hand?
Yes.
And again, this is what Galileo had trouble with, and you're going to have trouble with, because if I'm going 30 miles an hour down that road, I'm inside the car, I got this ball, and I go like this. Does it come back in my hand? Say, yes, I've done that. Why? Here's what other people would have said. They would have said, if you toss that ball in the air and the car keeps moving, it's going to hit you in the forehead. But what would Galileo would have said? He said, before I toss the ball up, what's the ball doing?
It's gone.
It's moving. And it has inertia in that direction. Now, just because I push it up, this was neat. Just because I push it up, does it cancel the inertia, the tendency to go that way? No. So what happens is, what would you see if you saw me at night and the car was going by there? You would see this. You would see the light go like this. Now, people have trouble with that. People have trouble. They say, I don't believe that. You're telling me the ball moved in a curved path? Yes, but not relative to the car. Relative to the car, the ball went up and down. That's all it did. But relative to the Earth's surface, what did it do? It kept its inertia going this way, and it went up and down. And so you would see that. Yes, no?
Oh, would it do that?
Now see, I know you have a little trouble with this, because imagine back there in Galileo's time, they would have had trouble also. And so it would just keep doing that same thing. See that?
Oh, because you're moving, yeah.
Now, here's the inertia part. Yes, he pushed it up, but what was it already doing in that direction? And it had inertia in that direction. And so even though I'm going to lift it up or let it fall down, it doesn't lose its inertia. And that's what people had trouble with. They couldn't understand the whole idea that objects have a tendency to keep moving in that direction if they're going in that direction. All right, so that's what happens here, and that's what that last paragraph is here. All right, now what I'm going to do is we're going to change gears a little bit, and let's see here. Okay, I won't do that one. Let's go to chapter 4. All right. Now what I did was I made you a packet, and this packet I'm going to use to teach with, and the bulk of the test, about 75% of it, is really on chapter 4. Am I going to have anything on vectors? Yes. Am I going to have anything on inertia? Yes. But the majority of it is this here. And I think the hardest part, the reason I'm going to spend a week, at least a week on this, is because it is the harder material. Now, I will tell you that when we first start out, it's not going to be that difficult. And then it gets harder. So I just need you to stay with me, okay? All right, let's take a look. And motion, we're going to study motion. And there are two words, vocabulary words that a physics person might use. One is called mechanics. We talked about that before, the study of anything moving and the cause of that motion. Now, kinematics would be, remember kinetic energy is the energy of motion? Kinematics is just the mathematical study of motion. If I just want to study the equation for motion, then it's called kinematics. Now, Galileo was really good at this. He was good at coming up with the mathematics, the kinematics, okay? But even Galileo, he was a genius. He had some ideas that were good, but he still didn't understand why some of those things happened. And it wasn't until Isaac Newton came. Newton was like born the year that Galileo died. So he would have been able to read Galileo stuff, but he wouldn't have known, they would have never known each other. And so I think more of Newton when I think about mechanics, and I think more of Galileo when I think about kinematics. All right, so here we go. Let's start the study of motion, and we're going to start with the very, very basic idea, but stay with me, okay? Stay with me with this. The easiest kind of motion to study would be study the motion in a straight line. Now, what physics people would say, they say we're going to study linear motion. A linear motion means you're motion in a straight line, so we're going to start out with that. Now, we eventually will talk about things that move in curves and stuff like that, but not right now. Uniform motion. Uniform motion is how a physics person would say that your speed is not changing.
Oh, but the direction.
Okay, just like a baseball team has a uniform because everybody looks the same, uniform means the same. So motion at a constant speed in a straight line. Okay, I'm going to stop till everybody's ready because if I lose you at the beginning here, I'll definitely lose you later. Now, what do you know about objects that are going in a straight line at a uniform speed? You already know something. They're in equilibrium, aren't they?
Yes.
What's the net force on these objects? Zero. Now, a special case of uniform motion would be sitting still, wouldn't it? So if a rock sits still, it has zero speed, right? That's kind of a special case of uniform motion, okay? Now, probably somewhere in the 7th or 8th grade, they may have at least introduced you to this, and math teachers also use this equation. It's called the speed equation, and it looks like this. Speed equals distance over time. Now, have you done that, something like that in math, or you remember middle school?
Yeah, it's doing some part of what we're doing now.
You're doing math now?
It's linear and angular speed.
Oh, you are?
Yeah.
Okay, that's excellent. That's excellent. So you're doing angular speed. All right, that's neat. Is that little W, that little funny
Omega. Yeah.
omega? That's omega?
Yeah, a lowercase omega.
Oh, lowercase, okay. Because the other one's used for electricity, for ohms. All right, so watch what I'm doing here. I'm going to, because it's called conceptual physics, I'm not just going to do that equation like they would in math. I'm going to do something different, okay? So what I'm going to do is take this equation, and I'm going to rearrange it a little bit. I'm going to rearrange it, and so I can see what it would look like without any fractions in it. Speed times time equals distance. Can everybody see that? Now, I don't mind. It's okay to memorize this. As a matter of fact, if you have trouble memorizing this, just think of a speed, 30 miles per hour. Try it again. 30 miles per hour. Oh, that's how I know that speed is distance over time. But now, remember they did the thing about proportionalities? Let me pick somebody at random. How about that? Patty, you can do it. Patty, tell me how any two of these variables are related as long as the other one is held constant. So tell me the relationship between S and D.
Directly proportional.
Real loud. What is it?
Directly proportional.
When?
When t is constant.
That's right. So if you said, go out in a car and drive for 5 minutes. Go out in a car and drive for 5 minutes. And one time you went out in the car and drove for 5 minutes at 20 miles an hour. And another time you drove for 5 minutes at 40 miles per hour.
Oh,
if the speed got 2 times bigger, what would happen to the distance that you would have gone?
2 times bigger?
2 times growing, wouldn't it? Okay, next one. Parker,
Yes.
tell me the
sir.
relationship between T and D.
It is, yeah, it's inverse.
But they're on opposite side of the equal sign.
No, but
Part.
are they direct?
Yeah.
I mean, they're
Parker,
direct
this is
proportionate.
Wait. Hey, so what do you think about T and D?
They are directly proportionate.
When?
When the S is constant.
Okay. So let's see what that means, okay? So now, ready? You're gonna drive at 30 miles an hour and you can't change it.
Yeah.
Now, if I let you drive for 5 minutes, you'll go a certain distance. What if I let you drive for 15 minutes? What if I let the time be 3 times bigger?
It would also get 3 times.
What would?
You say the time got 3 times bigger? The other one.
No, I need you to concentrate,
Both
okay?
of them will get 3 times bigger, but like whichever one you began with 3 times bigger, the other one get. I
What-
don't know what we began with to be good.
Wait. Let's start again. I asked you about T and D, and you said if S is held constant, that's why I covered it up.
Mm-hmm.
And I said you drove for 5 minutes and you went a certain distance. Then you went for 15 minutes. That's time. Time got 3 times bigger. You would go 3 times further. All right, ready? Okay. All right, let's go with Liam. Liam, tell me the only one left. What's the only relationship left?
Oh, come on, man.
Well, we've done 2 of the 3. There are 3 relationships here. Hang on. Which one have we not done yet? Which one? Between what and what? Yeah, same equation.
Between S and T.
All right, so tell me about S and T.
They're inversely proportional.
When?
When T is held constant.
Okay, so if we say I want you to drive 1 mile, and I say the first time you do it, I want you to drive at 10 miles an hour, and next time I want you to drive at 50 miles an hour. So if the speed gets 5 times greater, what will happen to the time?
It'll be 5 times smaller.
And what's another way of saying 5 times smaller? It would only take 1/5. It would only take 1/5 of the amount of time. I need to look at your faces because this is the easier material, and if I lose you on the easier material, I don't want to go to the next part. Got that? Are you okay on that? Everybody in this room, everybody should have been able to tell me about that equation before I taught it. That was a payoff. For us doing that proportionality unit, that's the payoff. So if I wasn't here teaching today, and you were just going to read this page, and you saw this equation, you shouldn't just say, oh, I guess I'll remember that equation. I want you to do way more than that. I want you to tell me the proportionalities that exist there. All right, now, what we have is, if we go to this page here, this is the page that talked about the speed equation, and we just got done doing that. And I do want to show you some speeds. And even though we're used to saying miles per hour, I would like you to look down here at this chart. See if I can get it on the camera. In physics, of course, we're going to be using meters per second. So get used to saying meters per second because that's going to be speeds, okay? I think as far as metric in English, the one you probably should know anyway is if you go around 60 miles per hour, you're going about 100 kilometers an hour. That's the one that you should be able to remember because if you do go to Italy next year, you know that 60 miles is about 100 kilometers. So if somebody says, hey, it's 100 kilometers to the next city, we're going to be on the bus for 100 kilometers. Oh, how far is that? That's about 60 miles, okay? Now, so if you think about that, when your car is going on the road at around 60 miles per hour, you're covering about 100 kilometers per hour, but that's about 28 meters per second. That means lay down 28 meter sticks and 1001. You would have gone 28 meter sticks in 1 second. Now, I'm not going to have you memorize these. We know how to use factory label. We can convert and things like that. So I'm not worried about that. This page here is the first time that you might get tricked up a little bit.
You said to stop you.
Oh, okay, all right,
Oh, you're stopping.
I can do that.
That's,
Yeah, we can do that.